Couple of more facts about integrals that we'd like to go over. Here is a fairly straightforward proposition. So let's let f and g be two functions that are both Riemann integrable on the same closed bounded integral R of AB. And then first fact is that if f is less than or equal to g, that is f of x is less than or equal to g of x for all x in this interval we're integrating over, then the integral of f, the integral of the smaller function, less than or equal to the integral of the bigger function. And then part B is that if f of x is bounded from above not by another function but by a constant, and this of course is also supposed to be true for all x in our little interval where we're integrating over, then the integral of f in absolute value less than or equal to m times b minus a. And then the proof of this so part A, so let's let P be a partition. And then the upper sum of f over that partition, we remember this is the sum of the lengths of our intervals xj minus 1, then the supremum over the interval but then if f is less than or equal to g, then the supremum of f cannot possibly be any bigger than the supremum of g. Anything that's bigger than all the g's is bigger than all the f's. And similarly, same thing works for the lower sums. It's just that the infimum of f is also got to be smaller than the infimum of g. I think I will not bother writing that out in complete detail. It's pretty much exactly the same thing. So the integral of f, that's the infimum of the upper Darboux sums. And then if each of those is less than the corresponding upper Darboux sum for G, then the infimum must be bigger, so that's less than or equal to the integral of G. And then part B, you just let g of x be m, or g of x equals minus m, and then minus m times b minus a. That's the integral from a to b of minus m. That's less than or equal to the integral of f by part A, because minus m is less than or equal to f. And then exactly the same thing again, except in the other direction. And that completes the proof. Next proposition, this one is a little bit more complicated. This says that the space of all Riemann integrable functions is a vector space. So you can add elements, you can multiply by elements. So that is if f and g are two Riemann integrable functions, and alpha and beta are real numbers, then alpha f plus beta g, that is also a Riemann integrable function, and the integral of alpha f plus beta g over our interval from a to b, that's alpha times the integral of f plus beta times the integral of g. So let's prove this, at least in the case of sums. That is the case where alpha and beta are both equal to 1. And the case of products, you can do this as sums and products separately. It's a little more efficient to state them all at once. You'll deal with products multiplying by constants on the homework. So let's suppose that f and g are Riemann integrable. So let's let P be a partition. And this is standard notation for this. All right, now let's write the upper sum of f over p. Let's remember our definitions. That's the sum from j equals 1 to n, xj minus xj minus 1, and then the supremum over this closed interval of f. And now let's go ahead and add the upper sum of g to this thing. And then when we combine our two sums, then we're going to add our two suprema. Now, let's think about this sum. We've got something that's bigger than all the values of f, and we've got something else that's bigger than all the values of g. So certainly, if you add them together, they're going to be bigger than all the values of f plus g. F of x plus g of x, that's less than the biggest f gets plus g of x, which is less than the biggest f gets plus the biggest g gets. So we can write this. Supremum of f plus g, and then we recognize that is the upper sum of f over our partition. And then similarly, the lower sum of FP plus the lower sum of GP, we're going to have an infimum instead of a supremum, and the infimum of F plus the infimum of G, that is less than or equal to the infimum of F plus G. So you can check that this is also true. So first we check that it's integrable. We'll use proposition 3.1.4 as usual. Pick a positive epsilon, and then by proposition 3.1.4, there is a partition P with upper sum of F over P minus the lower sum of F over P less than epsilon over 2. And you can do the same thing with G. Now, there is no guarantee yet that it gives you the same partition, and so instead of this P becomes a P, there exists PR such that these things are true. But then we just do our standard trick. We let Q be P union R, so Q is a refinement of both of them. So by proposition 3.1.2C in particular, the upper sum of F over Q minus the lower sum of F over Q, that's also less than epsilon over 2. The upper sum of G over Q minus the lower sum of G over Q, it's less than epsilon over 2. So just take the upper sum of F plus G minus the lower sum of F plus G. Then the upper sum is at most the upper sum of F plus the upper sum of G. Then the lower sum is at least, so minus the lower sum is at most minus the lower sum of F minus the lower sum of G. Then just rearrange it a little bit, switch these two terms around, and you'll see, oh, look, both of those are less than epsilon over 2, so the whole sum is less than epsilon. So by a proposition 3.1.4, F plus G is Riemann integrable on the interval from A to B. Now we just need to show that the integral of the sum is indeed the sum of the integral. So here is how we're going to do that. We are going to pick a positive number epsilon, and then integral from A to B of F, that is the supremum of the lower Darboux sums of F over partitions P So integral A to B F minus epsilon is not the supremum, is not the least upper bound, so it's less than the least upper bound, so it's not an upper bound at all. So there is a P such that the lower sum of F over P, it's greater than or equal to the integral of F minus epsilon, minus our little bit of wiggle room. Actually, I guess we can require that it be strictly greater than it. Similarly, the lower sum of G over R there's a partition such that the lower sum of g over that partition is within epsilon of the integral, and then we're going to let Q be their mutual refinement as usual. So the lower sum of F over Q, remember, taking out refinement raises the lower sum and lowers the upper sum. All right, then we remember we've got this inequality, the lower sum of F plus G over Q. That's at least as big as the lower sum of F over Q plus the lower sum of G over Q. So that's greater than the sum of the integrals, which is supposed to be the integral of the sum minus, we've got a little bit of an error. But we can make that error, we can make epsilon as small as we want. So the supremum of the lower sum of F plus G over Q, we can always find a partition Q that gets us bigger than the sum of the integrals. Minus a little bit of error, we can make the error as small as we want, so we've got that so we've got that equation. And then similarly, the integral is the infimum of the upper sum, and we've got an expression for the upper sum of F plus G that goes the other way. That's less than or equal to the sum of the integrals as well. And now F plus G is integrable, so we can use that fact too. So the integral is either the supremum of the lower sums or the infimum of the upper sums, or we can just use the fact that all the upper sums are bigger than all the lower sums. So the conclusion is that integral A plus B F plus G, that is either the supremum of the lower sums or the infimum of the upper sums. If you take the infimum of the upper sums, you get the sum of the integrals. If you take the supremum of the lower sums, you get at least the sum of the integrals. So we must have equality here, and that is what we were trying to prove, aside from the part involving constants, which is left to you as homework. Last thing we want to do in this section is we want to show that a bunch of functions, a broad class of functions, is indeed integrable. So we recall from the last lecture, I had this claim, what I was calling claim 3.1.8, to be consistent with how your book does it. If f is a function from a closed bounded interval to the real numbers is bounded and continuous, then f is integrable. F is Riemann integrable on that interval. And then here is the next claim in that series. If f is a function on a closed bounded interval, and it is bounded, and it is continuous except at the end point. And so it's continuous on the open interval from A to B. It doesn't have to be continuous at the endpoints. Then F is Riemann integrable on A to B. And let's go ahead and prove that. So we're going to use proposition 3.1.4 as usual. So let's pick a positive number epsilon. And now let's let little m and big M be the upper and lower bounds on F. So, well, because F is continuous by assumption, because F is bounded, we have that these are finite numbers. And let's let delta be the number epsilon our reader picked, and we'll divide it by 4 times big M minus little m, and let's go ahead and add a 1 into that just to make absolutely sure we're not dividing by 0, and actually we also want delta to be smaller than this number. We want it to be less than the length of our interval, or less than a third the length of our interval. Why did I do that? I did that because I am going to let's put an A twiddle on it. That's A plus delta. B twiddle is B minus delta. And because I require that delta is less than B minus A over 2, I have that A is strictly less than A twiddle. I'm adding delta, which is positive. But then A twiddle is strictly less than B twiddle, which is strictly less than B. And then F is continuous and bounded on this closed interval from A twiddle to B twiddle. So F is Riemann integrable on our closed interval from A twiddle to B twiddle. And then by proposition 3.1.4, as usual, there is a partition of this twiddle interval. Let's name the points. Let's have them start at x1 instead of x0, and that this is just a difference of notation, and end at xn minus 1, which is B twiddle, such that the upper sum of F over P twiddle minus the lower sum of F over P twiddle, we're going to force that to be less than epsilon over 2. Then we just let P be, we'll take P twiddle and we'll throw in the two endpoints. So now we have that A, if we let x0 equal A, that's less than our x1, less than x2, up to xn minus 1, which is less than xn, which is B. And then the upper sum of F over P minus the lower sum of F over P And then we just break this off. We've got the very first piece. We've got x1 minus a minus x naught. And then we've got a supremum and then we have the sum from j equals 2 up to n minus 1, xj minus 1. Point out that the very first term goes from x1 to x2. And then we have our very last term, xn minus 1. Then the supremum minus the infimum. And now let's see which of these pieces we can recognize. First off, x1 is a twiddle, x0 is a, and then I am too tired to keep writing these suprema all over the place. I'll just point out that the suprema is at most big M and the infima is at least little m. Then the second piece is the upper sum of f over p twiddle minus the lower sum of f over p twiddle. And then the last piece is b minus b twiddle, and then a big M minus a little m again, and then the whole thing. And then remember, a twiddle minus a is delta. So we've got a, and so is b minus b twiddle, so we've got 2 delta m minus m. And then this thing was supposed to be less than epsilon over 2. Then you just remember your definition of delta. This whole thing is less than epsilon. So by proposition 3.1.4, f is Riemann integrable on the interval from a to b, even if it's discontinuous at the endpoints. Very last result of section 3.1. This is theorem 3.1.7. Let's let f be a function defined on a closed and bounded interval. And if you're getting tired of those two bad, there are what we look at when we're looking at integration. Let's let D be the set of all points in AB such that F is not continuous at X. And let's suppose F is bounded and D is finite. And the conclusion is that if you're bounded and you've only got finitely many discontinuities, then you're Riemann integrable. This is not an if and only if statement. There do exist functions with infinitely many discontinuities that are still Riemann integrable, but usually being able to integrate anything with countably many discontinuities is good enough. And the proof, fortunately, we've already done most of work with. Let's let X be the set of discontinuities, and let's throw in the two endpoints. And notice that's a subset of AB. D is a subset of AB. A and B are obviously in AB. And it has the two endpoints and it's finite. So X is a partition of AB. And as usual, we're going to write X is little x naught, x1. We're going to name the points in order as usual. Then, if you pick any j between 1 and n, then f is bounded on the whole interval, so it's certainly bounded on xj minus 1 xj, and the endpoints are the only points of discontinuity, so it is continuous on the open interval. So that means that f is Riemann integrable on any of the little intervals. So, but a proposition 3.1.6, f is Riemann integrable on the entire interval from a to b. So continuous functions, or even finitely many discontinuities, means you're Riemann integrable. Very last thing I want to say in section 3.1 is not a theorem but a definition, and that's just some notation for if your limits of integration are in the wrong order. So if you've got a function that's Riemann integrable on the interval from a to b, then we define the integral from b to a of f as just negative the integral from a to b to f. And if you stare at the definition of partitions long enough, you can see that you could generalize it a little bit to make this make sense, but mostly what this does is it generalizes proposition 3.1.6. So we also define the integral from c to c of f to be 0. That also makes sense. Your partition would be the 1-point partition. xj minus 1 would be 0. And then we have that integral from, let's say, x to y of f. That's the integral from x to z plus the integral from z to y f, no matter what order. Or x, y, and z are in. So that's the real reason why we use this particular definition, why we like to have switching the limits of integration give you a minus sign. Now let's get into section 3.2. Section 3.2 has one big theorem and a couple of corollaries. So here is theorem 3.2.1. This is a theorem you have probably heard of before. And in fact, when you're doing calculus for engineers, when you want to actually evaluate integrals and not prove theorems about them, this theorem is actually much more useful than the Riemann some Darboux characterization because these are generally a lot easier to compute than Darboux sums. Let's let f be Riemann integrable on a closed bounded interval. And remember, we assume that Riemann integrable functions are all bounded. And we are going to define a new function. Capital F of S is the integral from a to s of f. And you may want to write that the integral from a to s of f of t dt. And then the conclusion is that then f is continuous on AB. And furthermore, if C is a point in the interval and f and little f is continuous, at our point C, then big F is differentiable at C. And big F prime of C is little f of C. And let's prove this. So we said that all Riemann integrable functions are bounded, so f is bounded. Let's let m be bigger than, let's say, the absolute value of x for all x. So we only really need capital M to be the upper bound minus M to be the lower bound. We don't really care much about keeping track of the two different pieces. And then if x and y are in our interval, then f of x minus f of y, that's the integral from a to x of f minus the integral from a to y of f. That comes out to the integral from little x to little y of f. You go from a to x and then from x to y. And this is by a proposition 3.1.6. And then the whole thing is less than or equal to the biggest f gets times the distance from x to y. And that is by proposition 3.1.10 part B. So f is Lipschitz. And that means by proposition 1.7.14, big F is continuous because all Lipschitz functions are continuous. And now let's think about the derivative. So let's let x be a point in our interval that's not our target point because we'll take a limit as we go to C. Then let's take big F of x minus big F of C over x minus C. Let's go ahead and subtract off our target, our F of C. Our thing we're trying to show is the integral. It is the derivative, sorry. That's 1 over x minus C. Then the integral from a to x of little f minus the integral from a to c of little f. minus f of c. That's 1 over x minus c. Comes out to the integral from little c to little x of f, and then we subtract off an f of c. And let's write this with a variable of integration. Let's call it f of t dt. And then let's take the integral from c to x. F of c is a constant dy. So by example 3.1.1a, this integral is just x minus c times f of c. This is supposed to be f of c, so let's divide by x minus c. We'll get an x minus c. We'll get just f of c. Then we combine the two integrals, and we can do that by proposition 3.1.11. Now let's use the fact that little f is continuous at c. So we're going to pick a positive number epsilon, and then by theorem 1.7.5, there is a positive number delta such that if t minus c is less than delta and t is in our domain, then f of t minus f of c less than epsilon. So if x minus c is less than delta and also is positive, and x is in this interval from a to b, then f of x, big F of x minus big F of c over x minus c, then minus little f of c. That's the absolute value of 1 over x minus c, integral from c to x, f of t minus f of c, dt. Then we're going to break that up, 1 over absolute value of x minus c, and then the integral is at most distance from x to c times epsilon, and that's by proposition 3.1.10b, because f of t minus f of c, that's less than epsilon everywhere. And then these things cancel out. So the conclusion is limit as x approaches c, f of x minus f of c over x minus c equals little f of c. So big F prime of c is a little f of c. And that's what we were trying to prove.